No, I mean, we have a few days before you have results. I think it's probably. But I put my biggest fear with that. Boundary condition, every single problem. Because technically, you have boundary conditions, it was an acquisition. You had to do it. It's the hollow circle. I guess the this is the yeah, exactly. So, I see how it's hard to that's the right attitude. It's for every conference. Spring break, even that. Spring break, what is that? Spring break, aka catch up. Catch up. Start my projects, I guess. I mean, the only time I remember my spring break semester was terrible. Last year. Yeah, are you talking about Thanksgiving break? Well, yeah, there was. It's just a little. Have you started that already? Yeah. On our section. I mean, they have everything up to the velocity. Oh, everything up until the numerical degree. Oh, yeah, that's the last. That's the last one. That's the. It's not too bad. Yeah, but just watching units. The velocity profile. No. You didn't really sit on the. Yeah. Right now. But the PowerPoint. No, you don't care. Yeah, that's the yeah, you have to.
Yep, clear for Friday. The thing that is due is the manual, the branching order, and then another branching.
Exactly.
Okay.
Yep.
All right.
Yep.
But then the need, lots of need.
Yeah, so you have to
Be careful about it.
Yeah, I just remember.
You see around so long. You have to make sure. Everyone's based on this, like, grabbing on something, you have to have your H that has well, there's not even no grade in here or really small.
I mean, then again, you do that.
There's like.
It's like you can have a
Sounds good.
So right now, it's just like setting your race for your color. Because you have to.
Yeah, I got sold. I was expecting salt on Thursday.
Well, I get it. Now I just start all the.
And it may not say like.
Go around there, yeah.
Yeah.
You haven't.
That's how I
Did you get it?
I want to show you.
Because I got it from the website, but it wasn't just from the website, so it's just like you're looking at this. Well, that's like they checked off. Don't even know that.
The thing is, like, if you ask her a question, she'll like, she won't even answer, like,
It's Friday, then you. I would have questioned. Learn that.
Yours was literally wrong, it's undefined. My whole. She said she worked on. She said she worked on software that was similar to software. She worked on that. But that's, she said she didn't like the back end stuff.
I don't know.
I know. She doesn't know. She yeah.
But even that. Put it in perspective, I can run it. That's like a. I don't get it. That's like.
Hey, it's the message. Oh, yeah, for sure.
I mean, I got a 45, but all this I've heard. Yeah. And I'm just trying to do it.
Yeah.
That one's well, then. Yeah, that's why. Yeah. Yeah.
Like I was like.
All right, it's 2:30, so let's go ahead and get started. All right, good afternoon, everyone. How's everyone doing today? Post midterms, or how's everyone feeling about that? All right, so I've started grading them, but I've literally just started, so I've only graded about 5 of them. So I think I'll probably have them ready by Monday. But as soon as I finish grading them, I'll put your grades up on Canvas, but then you'll get the exams back on Monday. Okay. And on the exams, I try to leave as much feedback as I can, so I can, so you can see, where I took off points and everything like that. Okay. But from the 5 so far, it looks good. So, but that's only 5, and so we'll see how it goes from there. Right. Okay. All right. Can we guys settle down a bit? We're going to start today. Okay. So the plan for today is we're going to continue on with our lecture notes on convection. And so we left off kind of in the middle of the intro to convection notes. And so I'm going to finish those up today. And then we're going to start our next set of lecture notes on external convection. Okay. Oh, that's kind of, let me pull this down a bit more. All right. So homework 4, I'm also working on kind of in parallel, and so I'm planning for homework 4 to be due basically right before spring break. And so spring break is going to be week 10 of the semester, and so we have after today just 2 more weeks of instruction until spring break, and so the next homework is going to be right before that. And so I'm hoping to get that out to you by either by end of today or sometime tomorrow, so you can guys start working. Okay? And that's going to cover basically this first 2 sets of lecture notes on convection. Yeah.
How many weeks in the semester?
There are 16 weeks total, but there are 15 weeks of instruction. And so one of those weeks is spring break. So we're in week 7 right now. And then, spring break is week 10. And then our last week of instruction is week 16. Wait a second. Almost halfway. Yeah. Wait a second. Not yet. We're about halfway. Well, we reach end game after the second midterm. That's the end game of the class. Oh, I did want to mention. So I think this is a good time to talk about it in this class. I want to talk about my grading policy. Okay. And so if you remember from the syllabus, I kind of made a vague statement about how I can adjust grades at the end. So let me give you some more specifics of what I mean by that. So I think this is a good time because everyone's thinking about their grade after the midterm. Okay. And so what I do at the very end of class, and I don't do this until the end, is what I do is I enter everyone's grades, and this is after the final, so after everything's in, and I look at the overall class average. Okay. And so I look at what that is. Okay. And what I usually like for my classes, especially for a class like this, which is, first of all, it's a required class. So, everyone is here because you're forced by the department to be here. But also I think this is one of the more difficult classes that we have in the department. And so what I like to have for my class average in here is about a 77% overall. Okay. And so what I do at the very end, if the class average is less than 77, and so, let's say that the class average is about 70%, what I'll do is I'll just add a flat amount of points to everyone's grades so that the class average becomes 77%. Okay. Right. So I find that this is kind of the simplest way to add to adjust grades because especially for this class because it's it's a difficult class you know, I think this is the first time we've all taken exams in person. So, you know, I want to give some flexibility in terms of that. Okay. And so that's what I plan to do. And so, you know, after the midterm's graded, I'll give you the average on the midterm. And then, you know, if you want to do kind of a calculation in your head, you know, if the average on the midterm is less than 77%, you can add that amount of points to your grade in order to get up to that point. Okay. All right. So there's someone's washing the window out there, just distracted me for a second. It's like it's not raining. Okay. But I don't do that until the end. And so, you know, I want to wait. I want to wait until, you know, all the midterm grades are in, all the homeworks and all the final exams are in. But that's what you can kind of expect for the grade adjustment in this class. Okay. All right. So are there any questions on that? Yeah.
Have you had any classes that their average is above 77%?
Oh yeah. Yeah. Plenty of times. Actually, the last time I taught this class, which it was purely a virtual class because that was a year ago, I think the class average was about 80%. But the last time I taught this in person, the class average was around 70%. And so I added 7 points to that. So, you know, the virtual instruction kind of inflates things a little bit. Is there another question over here? Yeah.
Would you say you make exams for people in person than online?
I try not to, but it's hard because and every exam is a little bit different because, you know, I have to, you know, come up with fresh new questions every time. And so, you know, looking at this exam and comparing it to the last time I gave in-person exam, I think a couple of years ago, I think this one was a little bit harder than that one. Now that I've kind of, you know, sat on it for a weekend and kind of looked at it. But, you know, but the grades so far have been pretty good. And so, you know, but I've only graded 5. And so we'll see. We'll see where it ends up. All right. Any other questions on this before we get started today? Okay. All right. So let's go ahead and get started. And what we were talking about last time was kind of an introduction to convection. Okay. Okay. And so we're kind of launching into a brand new unit in this class, you know, all centered around convection. Okay. And if you recall, you know, this whole unit, or a large part of this unit, is going to be centered around H. Okay. And what I mean by that is, you know, we're going to be learning ways on how we can compute H. Okay. Remember, H is our convection coefficient, okay? Which up to this point, you know, the convection coefficient has always just been given to you in the problem, okay? As if it were something that's kind of readily known, but you know, that's not really the case in reality. This convection coefficient is normally very difficult to obtain, okay? And so we're going to use, you know, some approximate methods in this unit, but in practice, you know, just know that this is pretty difficult. And the main reason it's difficult is that it not only depends on the thermal properties of the fluid, okay? Okay. But it also depends on the fluid mechanics. And so it depends on the flow, depends on the velocity profiles and all those things. And, you know, those things are traditionally very, very difficult to obtain. Because now you're kind of solving two problems at once. And so you're solving both the fluid mechanics problem as well as a thermal problem. And so that intersection between the two makes it, you know, very, very difficult to solve in practice a lot of the times. Okay? One particular aspect of the fluid flow that I want to talk about is whether the flow is laminar or turbulent. Okay? Is everyone familiar with the concept of turbulence? You remember that from your fluid mechanics class, right? Or at least you've heard the term before. There you go. Yeah, there you go. Yeah, that's basically how we measure turbulence. Is we check the Reynolds number. But another thing I want you guys to know is kind of what it looks like, right? And so let me kind of draw you a picture here. Okay. I'll draw you two pictures. Okay. Okay. And so let's say that we have a pipe here that has fluid flowing in it. Okay. Okay. And on the one hand, I'm going to draw you what a laminar flow would look like. Okay. On the other side, I'll show you what turbulent flow looks like. Okay. And so laminar flow, usually looks, the way laminar has gotten its name is because it looks like nice little lamellae sheets. That's literally why it's defined by that. Okay. And so if you look at the velocity, it follows these very nice kind of patterns where everyone kind of stays, in a straight line, and it looks very uniform and nice. Okay. Okay, and so another way that you can describe this is you can say the flow looks ordered. Okay. Turbulent flow, on the other hand, looks chaotic. Okay, and so instead of nice, straight velocity lines like that, you might get something like this. Okay. And so, another way that people commonly describe turbulent flow is that it's chaotic. Okay, it's not pure chaos, and so there is still some method to the chaos. And so even in turbulent flow, you have a net flow, right? So in the mean, right, or overall, you have a net kind of transfer of fluid in one direction. But if you look at kind of the micro scale, the velocity profiles are kind of doing all these kind of crazy things. So they're not just following a straight line. Okay? The analogy that I like to think of, when I think of laminar versus turbulent flow, is that laminar flow is what you get when you go to Best Buy on 364 days of the year. Okay, and so there's really not anyone there, and the lines are nice and orderly. Turbulent flow is what you get when you go to Best Buy on Black Friday. It's just pure chaos, right? Everyone eventually wants to go to the register, but getting there is kind of an ordeal. Yeah. Yeah, that's another way you can think of it too. Yeah. So yeah, any big shopping day you can think of as turbulent. We used to go to the store. I know nowadays people shop online, but now but people used to go to the stores. Okay. And so why does this matter? Okay. And so this matters because whether the flow is laminar or turbulent is going to have effect on our convection heat transfer. Okay. Okay. And so it's an important thing to note because it's going to have an effect on you'll see later it's going to have an effect on which formulas we end up using. Okay. And just like Pablo mentioned earlier, the way that we determine whether a flow is laminar or turbulent is by computing the Reynolds number. And so the formula for the Reynolds number is the following. Okay, so it has a symbol RE, One way that we can compute it is we can take the density, we multiply this by the velocity, okay? We multiply that by length, and then we divide that by viscosity, okay? Right, or another form for the Reynolds number that's popular is we just take, we take the combination of the viscosity and the density, and we form the kinematic viscosity, okay? And we do something like that, okay? All right, so let me go ahead and define these terms. So rho here is the density, okay? U here is a velocity. L here is some length, and how we choose that length is important depending on the, depending on the application. Okay. Mu here is known as the dynamic viscosity, and nu, which is the kind of fancy V here, this is the kinematic viscosity. And so what we do is, you would first compute the Reynolds number for your given flow. Okay. And if that Reynolds number is above a certain threshold, then we say that the flow is turbulent. Okay. And what that threshold is depends on what application that you're considering. Okay. I think Pablo mentioned a threshold 2200, so I think that's the threshold for internal flow, and so for flow that like I have up there. But for different applications, we have different thresholds, and so you have to look at what kind of application that you have and use the appropriate threshold for turbulence. Okay. All right. Any questions on this so far? Yeah. Oh yeah, for sure. And so density, the units for this is, I'm going to give you the SI units because that's what I can remember the most. Okay. So the units for the density is kilograms per meter cubed. For velocity, we have meters per second or length over time. Okay. For the length here, we have a meters. Okay. For the kinematic viscosity, we have meters squared per second. And then for the dynamic viscosity, I always forget this one. But let's work it out from here. Okay. And so for dynamic viscosity, we have a kilograms. Let's see what else. Meters. Kilogram over meters seconds. Let me write that over here. And so for dynamic viscosity, we have a kilograms over seconds meters, right? Yeah. So it's kilograms over seconds. I think dynamic viscosity has its other units called poise or something, but usually I just do it in terms of the base SI units. But basically, you need the units for these Reynolds numbers to cancel out. Okay. All right. Any other questions on this? Okay. All right. And so, what effect does this have on convection, right? And so I've said that, whether your flow is laminar or turbulent, that's going to affect your convection heat transfer, but how does it do so? Okay. And so to kind of illustrate that, let's look at what the velocity profiles look like for laminar versus turbulent flow. And so I'm bringing this up because if you remember from from last week, we talked about how the convection coefficient depends on the wall gradients, right? And so in other words, we had H. H was proportional to what the temperature profile looked like at the wall. Okay. And so in other words, the higher this derivative or the higher the slope of our temperature profile, then the bigger our convection coefficient is going to be. Okay. And so let's look at what these look like, for laminar versus turbulent flow. Okay. So let's start with the velocities. Okay? And so the velocities, remember, the goal for the velocities is to transition in between the condition at the solid versus the condition at the free stream, right? And so our velocity profile for laminar usually looks something like this. Okay? Maybe not quite that linear. Okay. Okay. Remember, this is our solid right here, okay? And then at the top here, we have the edge of the boundary layer. And so at the top here, we have, our velocity has reached the free stream. And so we say the velocity is u infinity, okay? Whereas at the surface, we say the velocity there is 0, okay? And remember, the whole idea with the boundary layer is that we have this smooth transition from 0 velocity at the surface to the free stream velocity at the outside of the boundary layer, okay? So this very nice, smooth transition. For turbulent flow, we still have a transition, okay? And so we still have to transition from u is equal to 0 at the plate, and eventually you have to equal to u infinity up there, okay? But the nature of the transition is a little bit different, okay? So it's not as smooth as in laminar flow. And so our transition looks something more like this. Okay. And so if you notice, the biggest difference between these graphs is that, the turbulent flow has a much sharper change near the wall. Okay. Okay. And that same trend applies for the temperature as well. And so this is for the velocities. And we can do the same thing for temperatures as well. And so for temperatures, we have our surface here. At the surface, we have some surface temperature Ts, okay? And then eventually, this is going to change, to whatever the free stream temperature is, T infinity, right? And so we have a nice smooth change there for the laminar flow. For turbulent flow, we have a much sharper changes. We have a surface temperature here. Okay. And so it looks more something like this, okay? And so that's really the big difference that you're going to see between laminar and turbulent flow is that, for turbulent flows, you see a lot sharper gradients or a lot sharper change, right next to the solid wall. Okay. And so we can quantify that. And so we can say that the dt dy at y is equal to 0 for laminar flow. Okay. This is going to be less than the dt dy at y is equal to 0 for turbulent flow. Okay. right? And you can just see that kind of visually from these graphs. And so, if you took the slope of the line, for the laminar case at the wall right here, okay, you're going to see a much bigger slope, in the turbulent case than you will for the, for the laminar case. Okay, and because of that, what you'll generally see is that the laminar convection coefficient is generally going to be less than the turbulent one. And so whenever you have turbulence, the net effect that that's going to have is that turbulence is going to generally enhance your convection heat transfer. And this is a trend that you'll see, throughout the entire unit. Okay, and sometimes it makes a big difference too. Right? And so sometimes, it can make, sometimes even like a 2 or 3 times difference, whether you have laminar or turbulent flow, in the amount of heat transfer that you can get. Okay. All right. And if you want, and so this is kind of the mathematical kind of, analytical reason why you get more heat transfer in turbulence, but there's kind of a more simple explanation for that. Okay, and so if we go back to our figure for what turbulent flow looks like, right? So turbulent flow is characterized by chaos, right? That chaotic flow will enhance mixing of fluid. Okay. Question. Oh, so the temperature slope is larger for turbulence. It looks the opposite for a y. Yeah. So, and it's a bit confusing because of the way I drew this graph. But what I'm talking about, the slope here is the rate of change. And so if you look at the rate of change in the turbulent case, we go from Ts and then we rapidly decay down to where T infinity is over here. But for the laminar case, then the change is a lot more gradual. And so when I say that the slope is different, what I mean is that the rate of change is a lot higher. And so if you kind of view the graph kind of sideways, then you can kind of see that slope effect. Mm-hmm. Yep. Wait a second. Yeah, so the wall gradient is just the rate of change of whatever profile you're looking at near the wall. And so if you took the rate of change here, then that's basically the wall gradient. Mm-hmm. All right, and so this trend of having more heat transfer and turbulence is something that you'll see, and we'll revisit these concepts again and again over the next couple of weeks. Okay, but intuitively, I think the easiest way to remember this is that turbulent flow means you have chaotic flow patterns, and those chaotic flow patterns will lead to better mixing of fluid, which is going to be ultimately better for your heat transfer. Okay. All right, any questions on this? Okay. All right. And so before we move on to the next set of lecture notes on external convection, I do want to talk about some of the non-dimensional numbers that we're going to have, okay? Because they're going to play a key role in our analysis here. And so you've probably come across dimensionless numbers, to some degree in your previous class. Right? We've already seen one today, and so we've already seen the Reynolds number. Okay. And so these dimensionless numbers, are always very useful in performing analysis. Okay. in particular, the main reason or the main area where you see dimensionless numbers being used is in an area called dimensional analysis. Okay. And what that basically, and so that kind of means a lot of things, but what that basically means for us is that we can use some experimental data that people have collected in the past and apply that to a wide range of situations. Okay. Okay. And so probably the class where you really dove into dimensional analysis is probably your fluid mechanics class, right? And the example that's probably given there is, if you do end up doing professional work with fluids, you might end up in a field like aerospace or automotive, automotive stuff, right? And so the thing is with those areas is that building prototypes is very, very expensive. And so if you want to test out like a new design for a rocket wing, it's really expensive to build a full-scale model of a wing and then test that in like a wind tunnel. Right? And so what you do instead is you build a much tinier wing. You build like a little baby wing instead. It has the same design, it's just much smaller. And then you run your experiments on a smaller wing because that's a lot easier to do. It's a lot cheaper to do. But if you want to take your experimental results from the tiny wing and apply it to the big one, you have to do some dimensional analysis. Okay? And the way you typically do that is that you present your analysis, you present your data in terms of these dimensionless numbers. Okay, and that's exactly what we're going to do here. And so what we're going to leverage in this convection unit is the fact that people have run a lot of experiments and they have a lot of experimental data on convection heat transfer situations. And so we're going to leverage that data by performing our analysis in terms of these dimensionless numbers. Okay. Okay. All right. And so because we're going to be working with these dimensionless numbers quite a bit, in this unit, I want to talk a bit about what they represent. Okay. And so a dimensionless number, it's never just developed just for nothing, right? And so the base requirements for a dimensionless number is that it has to have no dimensions, right? So that's why it's called a dimensionless number. But these are always crafted very carefully so that they're not just nothing. Okay. And so I say almost because I don't know if there's one that's out there that's not, but almost all dimensionless numbers represent a ratio of some kind. Okay. And so let's think about a dimensionless number that we've already seen in this class. Okay. And so we have the Biot number, right? And so the Biot number is the convection coefficient multiplied by the length divided by the thermal conductivity K. Okay. One way that we can interpret this is that we can say that this is like, 1 over K divided by 1 divided by HL, right? Right, and so the reason I put that like that is that 1 over K, this is almost the same thing as like the the conduction thermal resistance. Okay. And 1 over H times L, this is almost the same thing as like a convection resistance, right? They're maybe not the exact formulas, but they're close enough. Okay. And remember, we use this ratio, or we use this this ratio to explain whether we can use the lump the lumped capacitance method, in our transient heat conduction. Okay, and so this Biot number, which is non-dimensional, represents this ratio between how strong or how much the conduction resistance you have in your solid versus how much convection resistance you have. Okay. Let's look at another one that we've seen today. And so let's look at the Reynolds number. Right? And so the Reynolds number is U times L divided by mu. Okay. This also here represents a ratio. Okay? And in this ratio, what it represents is U times L is a way to express the inertial forces in the fluid flow. Okay. Inertial forces meaning the forces that have to do with motion of a fluid. Okay, right? Because if you have any kind of moving object, it has inertia, right? So if I threw a boulder at you, that boulder is going to have inertia. Right? And then on the bottom right here, you have viscosity. And so the viscosity here represents the viscous forces. Okay. Right. And so we use this ratio. And so if we say the Reynolds number is really, really large, and just like we mentioned earlier, if the Reynolds number exceeds a certain threshold, right? So let's say if it's 2200 for internal flow, then what we say is that the flow is turbulent, right? And so what that tells us is that turbulent flows are ones that have much more inertial forces compared to viscous forces. Okay. Right. And so if you think of your non-dimensional numbers here as a as a ratio, then they start to have some physical sense. Okay. Because whenever you have any kind of complex physical phenomenon going on, there are multiple forces or multiple things going on at the same time. And so if you compare the ratio of those different things, that gives you some information of what's actually going on underneath. Okay. And so we'll be using the Reynolds number a lot. And so this, this is important to know. But I want to introduce two more non-dimensional numbers, that we're going to use throughout this unit. Okay. So the first is the Nusselt number. And you're going to look at this number and you're going to think someone copied off someone's homework, but hear me out for a second. Okay. All right, so the Nusselt number is defined as H times L divided by KF. Okay. Where H here is the convection coefficient in a fluid. L here is some length, some characteristic length of the fluid flow, and KF here is a thermal conductivity of a fluid. Okay. All right. So you're probably like, wait a minute, the Nusselt number is H times L over K. We've seen that before. That's the Biot number, right? And so, I actually don't know the history, so I don't know if Biot and Nusselt were friends or whatever, but they look very similar. But there is one key difference between them, okay? And so for Biot number, when we usually compute this, we're usually computing this for some kind of solid, right? And so this thermal conductivity is usually for some solid object, okay? It's for some solid object, and the H here is for the fluid that's surrounding that object. Right. And so remember, that was our situation in transient conduction where we had, our little chunk of metal that's floating within a big pool of fluid. Right. And so the H and K refer to different parts. Okay. For the Nusselt number, this H and this K are referring to the exact same material. Okay. So they refer to the exact same fluid here. Okay. And so the way that we can interpret this is, is very similar to how we interpret the Biot number, okay? And so what the Nusselt number represents is a ratio of convection heat transfer to pure conduction heat transfer in a fluid. Okay. So it looks very similar to Biot number, but they are different, and that's why we call it we call them something different. Okay. All right. Any questions on this so far? Yeah. Yeah. So the H bar there is meant to represent an average convection coefficient. And so remember last time we said convection coefficient can vary quite a lot, in a solid, but this Nusselt number is kind of like an average. And so this H is actually going to be the most useful for us in our analysis. Yeah. Okay. All right. So that's Nusselt number. Next, we have Prandtl number. Okay. And so the Prandtl number is defined as the ratio of the kinematic viscosity to the thermal diffusivity. Okay. And so mu here is kinematic viscosity. And alpha here is the thermal diffusivity. Okay. Okay. Right. And so these two quantities here have the exact same units, and that's meter square per second. And so taking the ratio results in something that's non-dimensional. Okay. Okay. So what is it? So what does this represent? Okay. Remember we talked about last time how whenever you have a boundary layer situation, you have some kind of transfer of a quantity, through the boundary layer, right? And so from a fluid mechanical perspective, we talked about the transfer of momentum through the boundary layer. And for a thermal boundary layer perspective, we talked about the transfer of energy. And the main parameters that modulated these transfers were these two coefficients here. And so what this number represents is the ratio of how well momentum and energy can transfer within the fluid. Okay. Right, and that efficiency of how well how well momentum can transfer and energy transfer will have an effect on our convection coefficient. Okay. A more visual way to represent this, because that's kind of an abstract definition there. One way that you can observe this is that the Prandtl number tells you how quickly the fluid boundary layer and the thermal boundary layer will grow. Okay. Okay. And so I'll give you the three situations. Okay? And so if we have a Prandtl number, and so the Prandtl number is approximately 1, okay? And so the Prandtl number is approximately 1, then that means momentum and energy can transfer roughly at the same rate between the fluids, okay? And so in this case, the fluid and thermal boundary layers are almost the same. Okay? And so you'll mostly see Prandtl number equal to 1, mostly for gases. Okay? So most gases have a Prandtl number, maybe not exactly 1, but around 1. Okay? All right. Next, let's look at a case where Prandtl number is less than 1. Okay? Or in other words, Prandtl number is much less than 1. And so in this case, the thermal diffusivity has to be a lot higher than the kinematic viscosity, right? And so in these cases, energy is going to transfer a lot more easily. And if energy transfers a lot more easily, that means your thermal boundary layer will grow a lot faster. And so if I were to draw kind of an image of this, okay? So let's say that we have our plate here. Okay, we have fluid that's coming over here, and the fluid has some mean velocity and also some mean temperature. Okay. Right, so for a case when Prandtl number is much less than 1, if I were to draw the fluid boundary layer, okay, it might look something like this, where this here is delta. But because the thermal conditions or energy can transfer a lot more easily, the thermal boundary layer might look something like this. Okay? So this is thermal boundary layer. Okay. Okay. And so really small Prandtl numbers basically mean that your thermal conditions are going to develop a lot more quickly in this. All right. And so what kinds of fluids have really small Prandtl numbers? And so these are typically or kind of the most extreme cases that you might see this will be something like a liquid metal. Okay, so if you have like liquid mercury, something like that. Okay, we already know that metals can transfer heat or conduct heat really easily. And so it makes sense that they have really small Prandtl numbers. Okay. And so that's Prandtl number much less than 1. Okay. And then finally, we'll go over the case of Prandtl number much greater than 1. Okay. Right. And so Prandtl number much greater than 1, is going to be the opposite case. And so for Prandtl number much greater than 1, this means that the velocity boundary layer will grow a lot faster. Okay. And so if I were to draw the situation, we have our plate here. Okay. We have fluid coming in, U infinity, T infinity. Okay. So let's draw the thermal one first. And so the thermal one might look something like this. Okay, so we'll call it delta T. And the fluid one would just look much bigger. Okay. Or the fluid, so fluid and velocity boundary layer are the same. So I use the terms kind of interchangeably. All right. And so an example of a fluid that has a that has a Prandtl number much greater than 1 is oil, actually. So oil is a good example of a fluid that has, a Prandtl number that's much greater than 1. So I think, a lot of common oils will see Prandtl numbers like 10, or like 20 or 50, somewhere around there. Okay. And so that tells you, that momentum can transfer a lot more quickly.
Are you referring to weight or like the W part?
Wait, say again?
Like 10 W, 5 W 30, 10 W 20?
Oh, any oil. So any oil that's any kind of liquid that has quite a lot of fat or grease into it, then it has this property. Mhm. All right. Any other questions on this? Okay. So the nice thing about Prandtl number is that you very seldomly have to compute it. And so Prandtl number is at this point, because it depends purely on some material properties of the fluid, most of the time you can look up the Prandtl number in a table. Okay. Okay. And so probably by the end of this unit, you might forget what Prandtl number actually means because you're just going to get used to looking it up in a table. Okay. But the reason we can look it up in a table is because it purely just kind of depends on the material properties of the fluid. Okay. But it is good to remember what it represents. I think it'll make some of the other equations that we'll see later make a lot of sense. Okay. And this unit has a lot of equations that you'll see. Okay. And so it's a little bit easy to kind of get lost and trying to memorize all the equations and then kind of memorizing what each one means. And so, it helps to kind of have this knowledge here. Okay. And so that's a lot of non-dimensional numbers, right? And so how do we use these things in practice? Okay. And so the way that, these analyses are usually going to go, what we're usually going to aim for is computing the Nusselt number. Okay. The Nusselt number is really nice because it has our convection coefficient baked right into its expression. Okay. And so a lot of times we'll be playing a game of, how can we compute the Nusselt number for this situation? Okay. Okay. And the way that we're going to compute Nusselt number is we're going to rely on previous experiments. Okay. And so what we're going to see is that previous experiments have shown that the Nusselt number depends. It's a function of a lot of things, but it's a function primarily of two other dimensional parameters. Okay. Okay. And those two other dimensionless parameters are the Reynolds number and the Prandtl number. And so for a lot of cases, we'll have the following. So we'll have the Nusselt number. Okay. This is going to be a function of the Reynolds number and the Prandtl number. Okay. Right. And so if you've never seen this notation before, this fancy F, all it means is a function of. Okay. And the exact form of that function is going to depend on the situation that we're going to have. Okay. All right. And so the nice thing because we're a little bit disjointed, and so I don't have to leave it here, and so we can kind of jump right into one of those situations where you can see what that relationship looks like. Okay. So any questions on this before we jump into external flow convection? Okay. All right, so let's go ahead and jump right into it. All right, external flow convection. And so just like the line above it, basically states, the game that we're going to be playing over the next couple of weeks is, we're going to be computing this Nusselt number, okay? The difficult thing is that the exact expression or the exact formula to compute Nusselt number depends strongly on the flow situations. Okay? And so it's going to depend on the flow geometry. It's going to depend on the flow velocities. It's going to depend on whether we're laminar, whether we're turbulent. Okay. And so, starting with external flow convection, and then next week we'll start internal flow convection. We'll be looking at different situations, and then you'll see what the Nusselt number correlation looks like in those situations. Okay? And so we start with, a relatively simple situation of external flow. Okay. And so And so in external flow is defined as situations where we have flow over an external surface, okay? And the nice thing about the external surface, is that the boundary layer can grow unimpeded, okay? A really smart baby to be taking college classes. I wouldn't be surprised. Okay. And so actually, the geometry that I've already been drawing for you is one of external convection. Okay. And so the most classic and kind of the simplest external flow convection is if you have flow over a flat plate, okay, which is the picture I've kind of been drawing for you this entire time. All right. And so our flow over flat plate looks like the following. And so we have a fluid velocity that's coming in, right? We have this fluid has a velocity, it has a temperature, okay? And the important thing is that there's nothing above this, okay? So the flat plate's kind of by itself. And so when the fluid strikes the surface, then the boundary layer kind of just do its own thing, okay? And so it can keep growing and growing and growing for as much as it wants. Okay. Okay. Right, so let's talk about some examples of where you would commonly see external flow convection. Okay. And so, we have flow over a flat plate. And so, even though it looks simple, there's actually a lot of situations that can be modeled as that. Okay. And so I think probably the most common one, I think probably the coolest one will be like airflow over like a wing of some kind, right? So you have like an airplane, you have a rocket ship, right? You have airflow that's going over the wing. Even though the wing I know is not perfectly a flat surface, it can be modeled as a flat surface, okay? And so if you look at the boundary layers over an airplane wing or rocket wing, they look basically like this. Okay? And so some other examples that, and we'll go over a few of these in the class. We can have flow over a cylinder. We can also have flow over a sphere. Three is flow over a bank of tubes. And four, which is an interesting one, is four is what I like to call an impinging jet. And so I'm going to draw 1 and 4 for you. Okay, so flow over a cylinder might look like this. Okay, so we have flow that's coming over the cylinder. Right? And so this is a very common situation because a lot of times you're interested in insulating a pipe flow. Okay, and so I believe one of the problems, I think not on this one, or maybe the next one, is I have you talk about have you analyze. Let's say that you're living in a very cold area and you need to transfer hot water between buildings, how you're going to insulate that pipe and, how you can compute the convection coefficient on the outside of that pipe. Okay. Right, and the impinging jet looks something like this. And so, if you have let's say a water hose and you're spraying it against a wall, right? Well, let's say that you're spraying against the ground here. Okay. Right, and so the water is going to come out and it's going to deflect against the plate. Okay. This is another case of external convection because even though the flow is coming hitting the plate head on, eventually that flow is going to turn. And when that flow turns, you have an external flow situation because if you look at the flow situation over here, right, you have a situation where the boundary layers in that flow can grow, as much as it needs to. Okay, so it satisfies the conditions for external flow. Okay, and so if you read the textbook chapter, so the textbook chapter on this is really good, and so the textbook chapter goes over all of these situations. Unfortunately, because we don't have, we only have a limited amount of time in the class. I'm going to be focusing mostly on the flat plate example because I think that's the most, that's the most kind of widely applicable. And we'll also do the flow over a cylinder. But but the textbook goes over the sphere, it goes over the bank of tubes and the impinging jet as well. So if you're curious about how those situations can be modeled from a convection point of view, I would highly recommend that you take a look. Okay, any questions on this? Okay. All right. Yeah. Oh, the second illustration is for the impinging jet. Yeah. Mm-hmm. Yeah. So when you hear the term impinging, that means that you have a fluid flow that's kind of hitting something head on, and then it's hitting somewhere else. Yeah, exactly. Yeah. And so when thrusters come out of a rocket, it's a lot of those propellants are hitting the floor and then they're coming out like that. Mm-hmm. All right. And so just like, we mentioned before this, that, the way that we're going to compute, or, the goal for this unit is, we want to compute, or we want to have more accurate computations for what the convection coefficient is in these situations. Because a lot of times, we're not going to have it given to us. Okay? And just like we mentioned before, the way that we're going to do this is through the Reynolds number. Okay. Right. And so what we're going to find is that we're going to have formulas that relate the Nusselt number to, some other dimensionless parameters like the Reynolds number and the Prandtl number. And then from there, once we compute the Nusselt number, well, we can say that this Nusselt number is equal to the convection coefficient multiplied by the length divided by the thermal conductivity. Okay. We can then use that to compute what the convection coefficient is. Okay. All right. And remember, this functional form for the Nusselt number is going to change depending on our situation. Okay. So let's do our flat plate. Okay. And so people have done actually like millions of experiments on the flat plate just because it's so it's so easy. Okay. And so for a flat plate, flat plate flow, that's laminar. Okay. We have the following Nusselt number correlation. All right, so what we have is that the Nusselt number as a function of x is equal to 0.332 times the Reynolds number as a function of x raised to the 1/2 power times the Prandtl number raised to the 1/3 power. Okay. And this is equal to the convection coefficient multiplied by x divided by kf. But the last bit is just the definition for the Nusselt number again. But this is the formula that we're going to be concerned about. So the rest of it, that's just the definition for the Nusselt number. And so I just repeated it there but the formula that you need to compute Nusselt number is just the first part. Yeah. Mm-hmm. Right, and so this is, for all the buildup, that I think we've been having over the past week and a half, this is kind of, I think a little bit anticlimactic. And so, what I'm saying here is that all we need to do to compute the Nusselt number, and by extension, after we compute the Nusselt number, we'll have our convection coefficient. The only thing that we really need to compute is just the Reynolds number and the Prandtl number. Okay? Okay. And so if you can compute these two things, then you're good to go. Okay. But of course, it's not always as easy as it seems. Okay. And so the complicating factor for this is the fact that these dimensionless numbers, the Reynolds number and the Prandtl number, they have properties in them that depend on temperature. Okay. All right, so let's do a quick example just to kind of illustrate this. Or it's not really an example, but it's data to kind of illustrate what I mean. Okay. And so let's say that you want to compute the Nusselt number for water. Okay. Okay. And so to compute the Nusselt number for water, right, you're going to need to compute the Reynolds number. You're going to need to compute the Prandtl number. Right? Both of these things depend on the viscosity of the water. Okay? And so if we look at our formula for the Reynolds number, remember this is U times L divided by mu. And of course, that's not an equal sign, sorry. And of course, the Prandtl number is equal to the mu multiplied by the thermal diffusivity. Okay. And so in both situations, we're going to need to use the viscosity in order to compute, these two things. And so naturally, what you're going to do is you're going to look up, you're going to Google water viscosity, right? And you're going to plug in what you see. Okay. But what you should see is something like this. You're not going to see just a single value for viscosity of water. You're going to see a data table. Okay. And so if you look at the table, you'll see that the viscosity here depends on whatever temperature the water is. Okay. And so if you have a temperature that's freezing, basically, so if that's 0 degrees Celsius, then the viscosity is 1.787 meters squared second. Okay. But if you increase the temperature to 5, then the viscosity also increases, or decreases, I'm sorry, to 1.519 meters squared per second. Okay. And this trend continues on. So you go up to 10 degrees C, begins at 1.307. 20 degrees C, 1.004. Okay. 30 degrees C becomes 0.801. And I'll do one more. So let's do 40 degrees C, 0.658. Okay. So this is not uncommon at all. In fact, it's very common. And so what you'll see is that a lot of the properties of our fluids, they depend strongly on temperature. Okay. And so you might be looking at that and you're like, okay, that's fine. We'll just see what temperature our fluid is and then we'll compute the properties, right? No problem. The problem is, the problem here has to do with the fact that we're dealing with situations with very different temperatures, right? And so let me give you kind of an extreme case. Okay? And so let's say we have a really, really hot plate. Okay? And so it's so hot that the temperature of the plate, we'll say is 100 degrees C. Okay. And we're going to be flowing water through it. Okay. And so the water is going to be meant to cool the plate. But let's say the water is at a temperature of 10 degrees C. So it's pretty cool. Okay. And of course, because we have these two different conditions right here, a boundary layer is going to form. Okay. And we know that the purpose of the thermal boundary layer is to act as a transition between the solid temperature and the fluid temperature. Okay. And so in this situation, we need to compute the viscosity, okay? But what temperature do we use, right? So do we use the fluid temperature out here? Okay. Right, that's one possibility. But but we know that the convection coefficient depends really strongly about on the conditions at the wall. Okay. So then does it make more sense to use the solid temperature to compute the properties? Okay. Right, or maybe it's something in between, right? And you can see here, it makes a big difference, right? And so I don't even have 100 degrees C here, but then, if we make the difference between, 10 degrees C and even 40 degrees C, right? The difference between this is like a 2x difference, basically, right? And so what we choose for the temperature here is going to make a really big difference on our results, okay? And so the solution to this is to, probably do what you're probably thinking of right now is just to split the difference. Okay. And so we define something called a film temperature. And so the film temperature, TF, is just going to be the average between the surface temperature and the fluid temperature. Okay. So it's going to be TS plus T infinity divided by 2. And then we're going to use this film temperature to evaluate the fluid properties. Okay. All right, and so for this particular case, our film temperature is going to be 100 plus 10 divided by 2, and so that's going to be 55 degrees C. Okay. And so when we go to compute our Reynolds number, we're going to use the viscosity of water at 55 degrees C. Okay. So that's really important. And so, the properties and what we evaluate them at is going to be, really important for us going forward. And so it's important that we compute this film temperature to make sure we get the correct property values. Okay. All right, any final questions on this before we wrap it up for the week? Yeah. No, so I mean, I didn't list the thermal diffusivity here, but that would also depend on the temperature. Yeah, so it all depends on temperature. Okay. All right, and so that's all I got for this week. And so next week we'll continue on with this set of lecture notes. By Monday you'll have your midterm scores, and so you look forward to that. All right, so have a great weekend, everyone. If you have any other questions about anything, please don't be afraid to reach out, and I'll see you guys next week. Kang, any final questions before I wrap up the Zoom call?
No.